Good evening. I'm Spot On Weather meteorologist Matthew Euler, and welcome to the Spot On Weather How the Weather Works training video. This is part 6 of the training series. On this particular title slide tonight, I'm showing an upper level weather chart, and within this chart, there's a lot of different data you can get from this type of chart. And I am going to go over some of those processes that occur in the upper levels of the atmosphere. Later video, I will get into how the surface features connect to these upper level features or these upper level processes in the atmosphere. But for this particular video, part 6, I know you're going to enjoy it. I'm going to break this down really in simplistic terms. And let's get started. I'm excited. Let's do it. All right, so the first thing we're going to talk about tonight is a process that's called convergence and a process that's called divergence. So I want you for a moment to consider a volume of air with invisible but defined boundaries. Okay? Convergence is going to occur when the total amount of air within this specific volume tends to increase. And I always like to use the analogy of driving on the interstate in a car, and maybe 2 miles out, you're still at 50 miles per hour, you're doing 50 mile per hour speed in your car. But as you get closer to the toll booth, you see that slower speed sign come up, where you slow, you decelerate, and you reach the toll booth, and there's a bunch of other cars ahead of you. So at a toll booth, you have a convergence or an accumulation of cars. And a similar thing occurs when we talk about atmospheric convergence, except now we're just talking about an accumulation of air in one particular area. Divergence, on the other hand, is the opposite effect. This occurs when that total quantity of air tends to decrease or spread further apart. And for divergence, I like to use the analogy. Let's say you went through the toll booth, you paid your toll, now you're starting to accelerate again on the other side of that toll booth. Meanwhile, the cars that were ahead of you that already paid, they're accelerating, increasing their speed well far away from where you're at. So we have a spreading apart of cars. And this is known as divergence, a spreading apart of the air. Now both convergence, the accumulation of air, and divergence, the removal or spreading apart of air, can be broken down into both directional and speed components, which can tend to act together or actually act to offset each other. I'm going to show you some examples here in a moment. When we talk about the atmosphere, we talk about convergence and divergence. So let's first take a look at directional aspects of convergence and divergence. So when we talk about directional convergence, this is also known as confluence. This typically occurs in the upper atmosphere on those upper level charts when two height contours, they funnel or get closer together. This is directional convergence. The wind is coming together at a point. Air from various directions seems to flow inward towards that single point. That's directional convergence. When we talk about directional convergence is also known as confluence. On the other hand, when we have directional divergence, this is also known as diffluence. This indicates that air from a specific point source is flowing outward into various directions away from that single point. Now let me go ahead and get my drawing tool here, and I'm going to point out 2 examples here. Okay, so the first example here in the graphic on the bottom, this top 3 blocks, this represents the process that's known as convergence. More specifically, this is at directional convergence or confluence. So initially what we have is we have these wind barbs. By the way, let me explain the wind barbs here briefly to you. When you have a full barb, that is indicative of 10 knots, and a half barb is 5 knots of wind speed, okay? So in this particular example, on the top far left of the 3 blocks, we have air that is generally flowing towards each other to a single point. This is known as convergence. And this particular wind barb is represented by a westerly wind at 15 knots. And this particular wind barb is an easterly wind at 15 knots. And so at this point, right where my red dot is, that's the point, the single point of directional confluence, the coming together of air at a specific point due to the direction, the wind direction. Now let's take a look at, examine the second block here. Notice that the winds are generally coming together. So the wind barb is pointing from the southwest here, indicating a southwesterly wind. We have a westerly wind at 15 knots in the middle, and then we have a northwesterly wind at the top. And whenever all three of these winds converge, right where my red dot is, that is the directional confluence or directional convergence. Air is coming together. There's an accumulation of it. Another example of directional convergence or confluence is this particular image. Right where my red dot is, once again, represents that single point, that single focus point for how the wind is coming in and converging to that point. Okay? In this particular image, we have a northerly wind at 15 knots. That wind barb is coming from the north. We have an easterly wind coming at 15 knots, blowing at 15 knots. We have a southerly wind at 15 knots, and then we have a westerly wind at 20 knots. All the air is moving towards a single point in the center. This is indicative of directional convergence or confluence. Now let's take a look at the bottom here. These three blocks represent examples of divergence, more specifically difluence, directional divergence or difluence here, the three bottom blocks. Right, so the first example here on the bottom left, we have a wind barb pointing from the west, and then we have the wind barb pointing towards the east. The wind is basically blowing opposite to each other. So at this particular point in between the wind barbs, we have a spreading out of the wind, that difluence occurring. The next particular graphic here, next block, if I were to put my red dot right at that location, you'll notice that we have a southwesterly wind, a westerly wind, and a northwesterly wind. Okay. Generally, we have a fanning out of these wind barbs right here specifically. We have a southwesterly wind and a westerly wind. So in this particular area, we have difluence. And then finally, this third example also shows a directional divergence of the air or difluence. We have a southerly wind at 15 knots. We have a westerly wind at 20 knots, a northerly wind at 15 knots, and then an easterly wind at 15 knots. Now in general, we're sitting at this point here. We have the air spreading out away from that single point of focus. So these are all examples of either directional convergence or directional divergence. Okay? Now, in addition to directional convergence and divergence, we have to look at the wind speeds. Speed convergence occurs when air parcels travel from regions of higher velocity to lower velocity. Now this would be that toll booth example. When you're slowing down to approach a toll booth, you may have a line of cars ahead of you. We're getting an accumulation of cars because of the speed differences. They're already creeping through the toll booth while you're just decelerating coming up to the toll booth. So therefore you have an accumulation of cars, a longer line of cars. And so same thing happens in the atmosphere. Here's an example of speed convergence in this left-hand block. If this is the point I'm analyzing where the red dot is, I have a westerly wind at 15 knots, and then I have a westerly wind at 30 knots. So I got much faster wind speeds here, blowing into slower wind speeds at this point. So right in the middle there, I have speed convergence. On the other hand, speed divergence occurs when air parcels enter regions of higher velocity. So this would be the example of the toll booth again, except those cars out ahead are now picking up their speed again as they leave the toll booth, and you're still back there paying at the toll booth, and then eventually you come out of the toll booth and you start accelerating yourself. But in general, in this case, we have 30-knot westerly wind, and then we have a 15-knot westerly wind. So 15 knots of wind blowing into 30 knots of wind. this results in speed divergence. So speed convergence, speed divergence, directional convergence, these three examples, due to wind direction coming together at a single point, and directional divergence due to wind direction, the wind coming apart, blowing away from each other at a specific point. Now, the spacing and the shape of isobars, if we're on the upper level charts, the spacing and shape of those height contours or iso heights, as well as the strength and location of the jet stream, are going to determine what type of airflow results. Confluence, remember that's the directional coming together of the wind, that describes airflow that appears to funnel inward, while diffluence, that's spreading apart, refers to airflow that does just that, spread apart. Now, look at this particular image in the bottom right portion of the slide. Let's go ahead and analyze this. Okay? The solid black lines on this graphic represents lines of equal height. They're iso heights or height contours. So I have a 540 decameter height contour everywhere along this solid black line. I have a 546 decameter height contour, iso height, everywhere along this point, the center dark line here, solid line. And then I have a 552 decameter height contour or iso height, generally the solid dark line at the bottom. Okay? And then I have my wind barbs again, which indicate my wind speed and direction. Okay? So let's look at this. So initially, if I'm at this point right here, right at this where I got the red dot in the graphic, I have a northwesterly wind at 20 knots. I have a southwesterly wind at 20 knots. But notice how I have a northwest wind coming together along this particular line, and I have a southwesterly wind coming in along this specific line. So I have what's known as confluence due to the direction. A northwest wind and a southwest wind are meeting or converging at this point. Now let's go over here at this far right part of the graphic. Now let's analyze what's going on here with the direction of the wind. In this particular wind barb, it's indicating a wind direction from the southwest at 20 knots. And at the bottom here, this wind barb indicates a wind direction from the northwest at 20 knots. So I have a wind from the southwest at 20 knots, and I have a wind from the northwest at 20 knots. And so southwest and northwest, the direction of the wind is spreading apart, moving away from this point, this red dot I have here on the graphic. That is an example of directional divergence or diffluence. Okay? So we have an accumulation of mass here based on wind direction, and we have a removal of mass at this point based on the directional divergence. So adding mass, subtracting mass, and when I say mass, what I'm referring to is accumulation of air in the upper levels. By the way, this particular graphic is depicting the height contours and wind speed and direction at 500 millibars or 18,000 feet above the ground. Now, let's analyze this graphic for speed convergence and speed divergence. All right, so let's examine these particular wind barbs in relation to these two center wind barbs. All right, so I have 20 knot winds at both of these locations, and they're blowing in to 50 knot winds in both of these locations in the center of the graphic. Whenever you see a dark black flag like that, that indicates 50 knots of wind speed, by the way. So I have 20 knots of wind blowing into 50 knots of wind. So what do you think is going to happen there? The wind is, in this particular point between the wind barb sets, I'm going to have speed divergence because I'm having 50 knots of wind move away from this particular location. I only have 20 knots of wind coming in to replace it. So that's speed divergence. What happens on the other side here? Right here in the center again, these two particular wind barbs represent westerly winds at 50 knots, the black flags, and then I have 20 knot wind speeds over on this direction on these two wind barbs. So now I have a case where I have faster winds blowing into slower wind speeds, and that's going to result in speed convergence or accumulation of mass in this location between the wind barbs. All right? But now, you can't just look at the speed divergence, convergence, and directional divergence, convergence, and necessarily get an idea of what's happening in the upper levels of the atmosphere. In order to assess the effects of convergence and divergence, the combination of the speed and direction factors must be taken into account. And what you're really going to look for on an upper level station plot is the height tendency. Are the upper level heights rising or falling? So if the upper level heights are rising, that's generally going to indicate what's known as speed convergence or an accumulation of mass. So if your height tendency is positive or rising, you are seeing some sort of convergence, whether it be directional or speed. If you analyze the height tendencies on an upper air station plot and the heights are falling, you have a negative sign in front of the heights, that generally indicates a divergence process in the upper levels of the atmosphere. And you can actually get two things to counteract or offset each other. So for example, at this point right here, I had confluence, but I also have speed divergence. So confluence, due to wind direction coming together, would indicate a height rise. But then I have speed divergence at the same point. So confluence, height rise, speed divergence, a height fall. So I would need more information to know what's really happening at this point. Now if I look over at this location, I have diffluence, the spreading apart of these wind barbs, but I also have speed convergence, where I have faster moving winds blowing into slower moving winds. And these two offset each other. Diffluence would give you a height fall, while speed convergence would give you a height rise. So it's important to look at the height tendencies. Are the heights in the upper levels at a particular station rising or falling? Because sometimes this happens in the atmosphere and you get opposing, opposite effects. Right, so now let's talk about why is upper level convergence and divergence so important. Not only that, but what about the low levels of the atmosphere? How is this sort of connected? And so at the low levels of the atmosphere near the Earth's surface where we live, we are constantly seeing the effects of surface high pressure systems, the blue H, and surface low pressure systems, this red L. Think of the high pressure as fair weather, and this red L as a storm system of poor weather. So we have a case within the center of a surface low pressure system of what's known as low level convergence. Notice how these blue arrows are all moving, working their way inward towards the center of low pressure. Notice how these blue arrows come together here at that center of that low pressure. That indicates the air in the low levels of the atmosphere is converging. There's an accumulation of air here. Now, as air converges in the low levels of the atmosphere, it has to go somewhere, so it rises. That rising vertical air motion is denoted by these red arrows. Now, I'll get more into depth about how this all connects in a future training video, but there generally tends to be an area of upper level divergence located above an area of low level convergence. So you have opposite effects going on in the atmosphere if you look in the three-dimensional aspect. At the surface, you'll have, with a low pressure system, you have low level convergence, upper level divergence. Okay? Now let's examine the high pressure system over here. In this case, look at the blue arrows. The air is moving clockwise and outward away from the center of the high pressure at the surface. This is an example of low level divergence. Now, as the air spreads out at the surface, the air from above comes in to replace it. So higher up in the atmosphere, you have a sinking air motion all the way down from the upper atmosphere to the surface to replace the air that is diverging or moving away from the center of this high pressure. And then in addition to that, you have convergence aloft. So with high pressure, you get low level divergence, and then the opposite effect above that, upper level convergence. So you have these direct and indirect circulation cells that may set up from the surface all the way up high above the ground. And with that being said, we have to take a look at a couple effects here. The first one is known as a chimney effect. Now what happens here is converging airflow at the surface, low-level convergence, causes an accumulation or piling up of air that generally tends to result in rising vertical air motion. And as this air rises, a net transport of air higher up aloft encourages lower surface pressure with air accumulating aloft. And the surface pressure continues to fall or decrease, and that encourages continued inflow towards the center of surface pressure and increased levels of low-level convergence. And unless some process removes this upward rushing air from the top of the column, it will eventually back up and fill the surface low. This is known as the chimney effect, by the way. Now, if you get a jet stream aloft over a surface low, some sort of divergent airflow, perhaps is associated with positive vorticity advection, this is going to remove the rising air. The circulation then will perpetuate itself in a repetitive cycle. Air is going to pile up or accumulate at the surface. It's going to meet and converge, rise in the vertical, and then it's removed at the top of that air column. Low pressure created at the surface by this vertical motion maintains converging airflow continually, feeding the vertical motion in the air column until the removal of air aloft ceases. Now, if the outward flow from the top of the column increases, the air rushes out of the top of the column more quickly, then you get a much stronger, intense, deepening surface low pressure system that increases surface convergence, almost creates a suction effect, and that further enhances vertical air motion. Again, this process is known as the chimney effect, and the correct combination of either difluent flow patterns due to directional divergence aloft or speed divergence associated with a jet stream. Now, I did briefly do training, earlier video of the How the Weather Works training series when I did the training on jet streams. I talk about a special type of feature, accelerated region of wind within the jet stream core known as a jet max or jet streak. You get speed divergence associated with certain quadrants of that jet streak. The left front and the right rear quadrants are the divergent quadrants of the jet streak. And if you have an area of low-level convergence, surface low pressure, the air vertically rises, and you get that jet streak overhead, the favorable quadrants of the jet streak, the upper left and right rear quadrants, that'll act readily to remove that divergence, increase the divergence aloft or remove the mass aloft or the air. And that will result in a much more intense surface cyclone. Okay? Now take a look at the chimney effect here. In this case, in the upper levels, we have a westerly wind at 50 knots. There's that black flag again, that's 50 knots. And then we have another wind barb at 50. And remember, just the full lines are 10 knots each. So this would be a westerly wind at 90 knots. If I were to look and examine what's going on right at this point where I have the red dot, I have, again, 90 knots and I have 50 knots. So I have slower wind speeds, right? I have slower wind speeds moving into faster wind speeds. So that is generally going to result, faster's out here, blown away, slower's coming in. That's going to result in speed divergence. Notice the direction of both of these barbs is from the same westerly direction. So I do not have difluence, I have speed divergence due to speed differences between these 2 points, higher aloft, above the surface low. So speed divergence is going to favor the removal of mass aloft, and at the surface, if I have an accelerated rate of removal of mass aloft due to this divergence, if this is acting faster, the mass is being removed aloft faster than what's being replaced in the low levels, this low-level convergence will continue to increase, and the rising air motion will become more vigorous. The surface pressures will fall rapidly with this surface low pressure system, and you will have a significant cyclone on your hands, as well as potentially severe weather. So again, look at the chimney effect. Opposite effects here. Low-level convergence and upper-level divergence. That's the chimney effect. Removal of mass aloft over a surface low pressure system. Now let's take a look at the opposite effect, the damper effect. Now, the opposite effects occur. Now in the upper levels, the atmosphere or aloft, we have excessive upper-level convergence resulting in an accumulation of air or mass at the top of the column as compared to diverging air at the bottom of the column. So in this case, let me get through these first and then I'll explain the diagram. Bottom line is, if the accumulated mass is coming in at a quicker rate at the top of the column as compared to the bottom, vertical air motion is going to basically act downward, resulting in the damper effect. The correct combination of either confluent flow patterns, that's due to that wind direction coming together, directional confluence, aloft, or speed convergence associated with the jet stream, those jet streaks again, this supports the process, results in fair weather. So damper effect, think fair weather, and for chimney effect, think a storm or bad weather. So let's take a look at this diagram at the bottom. So in this case, with damper effect, we have this is going to be more of the confluence or directional convergence at this point, at the top of this column. So we have a southwesterly wind at 50 knots, but we have a northwesterly wind at 60 knots, and they're converging along this common point above the column, at the very top of the column of air. So this is an example of confluence or directional convergence at this point. So we're accumulating mass aloft at the top of this column of air, all right? As this air accumulates, if the amount and the rate at which this accumulation occurs, if it exceeds what's going on here at the surface with divergence or spreading apart of air, then you're going to have a greater acceleration of downward vertical motion, and whenever the air sinks in the atmosphere, it dries out and warms, and it results in generally fair weather. With a damper effect, we just flip things around. In the upper levels of the atmosphere, at the top of the air column, we have generally we have convergence aloft, and we have divergence at the surface. And whenever you get this accelerated air motion downward, it also acts to increase the weight of the air column at the surface, resulting in that rising barometric pressure. Mostly clear skies, light winds is typically what you see with a high pressure system or an anticyclone. So this is the damper effect, okay? Convergence aloft over divergence at the surface. All right, so as we go up in the atmosphere above any type of pressure system, whether it be high or low pressure systems at the surface, there is a very important line or level in the atmosphere that's known as the level of non-divergence, or LND. And in the atmosphere, an inflection point exists at which the convergence will switch or change over to divergence. If we were talking about a low pressure system with low level convergence and upper level divergence aloft over it, then we would be talking about convergence in the low levels changing to divergence in the chimney effect. So at this point where that convergence divergence switches or changes, that is known as the level of non-divergence, where convergence and divergence are both equal to zero, and the vertical velocity at this level of non-divergence actually reaches a maximum, whether we're talking about downward motion or upward motion. And the level of non-divergence at LND normally exists between 600 millibars and 500 millibars. Now, just for reference, 500 millibars is 18,000 feet above the ground. 600 millibars is going to be about 14,000 feet above the ground. But in general, if we look at the diagram here in the bottom, we have a case of surface high pressure, generally here on the left. Hopefully you can see the H there, the letter H, high pressure. And then there's a letter L in dark black letter here over in this location representing low pressure. So the level of non-divergence is this dashed horizontal line. And you'll notice when we talk about with low pressure and the chimney effect, where we have low level convergence and upward vertical motion, rising air motion, the rising air motion is going to reach its strongest point at this level of non-divergence, this dashed line. And the processes are going to switch from convergence below the LND to divergence above the LND when we're talking about the chimney effect and low pressure at the surface. For the opposite damper effect, we have upper level convergence, and we have sinking air motion, and the greatest sinking air motion is going to occur right there at that level of non-divergence. The air is going to continue to sink, and that LND is that transition line between upper level convergence and lower level divergence. That's the damper effect. So there is that line between 600 and 500 millibars in the atmosphere, 14 to 18,000 feet above the ground, known as the level of non-divergence. What is so important about this level? This is the point at which maximum vertical velocity is achieved. Additionally, we must talk about something that's known as the isopycnic level. Iso meaning equal, picnic meaning density. So at roughly about 350 millibars, which is pretty high in the atmosphere, generally it's going to be above 25,000 feet above the ground. At that level, density remains fairly constant. And that level of equal density, isopycnic level, is what it's called. If we maintain constant density, in order to do that, it requires temperature changes to balance pressure changes. So if pressure were to increase, so must the temperature, and vice versa. So if pressure decreases, temperature must decrease. If pressure increases, temperature must increase. It's a directly proportional relationship. Changes below that level of constant density, the isopycnic level, they must be balanced by changes above it to maintain that constant density. All right, so that was a quick update or a quick introduction to isopycnic level. So we talk about level of non-divergence. We talk about the changeover from convergence to divergence between the low levels, the upper levels of the atmosphere. Just wanted to quickly introduce you to isopycnic level, level of constant density, and the fact that pressure changes must occur along with temperature changes both above and below this level in order to maintain that constant density. Now let's talk about vertical air motion a little bit more. Vertical air motions generally tend to produce heating and cooling via adiabatic changes. Rising air generally experiences adiabatic cooling, and subsiding or sinking air generally experiences adiabatic warming. Now, moisture will slow the cooling process of rising air. We talked about this in a previous training video. I believe it was the last video, part 5. We talked about the overall effects of air parcels rising at the dry adiabatic lapse rate, 10 degrees Celsius per kilometer, and then once the temperature and dew point are equal to each other, as the air parcel rises and cools, eventually the air temperature reaches a dew point temperature, saturation is reached, and then from that saturation level, higher up, the air parcel is now going to cool at a slower rate at 6 degrees Celsius per kilometer, known as the moist adiabatic lapse rate. Why is the moist adiabatic lapse rate generally less compared to the dry adiabatic lapse rate? It has to do with the release of moisture to the surrounding atmosphere through the process of condensation. We call this the latent heat of condensation, where heat is liberated or given off to the surrounding air as a parcel undergoes saturation, conversion from a water vapor to a liquid. All right, one more look here, courtesy of weather.gov, showing you the differences between the chimney effect and the damper effect. In general, with a chimney effect, again, you have low-level converging air at the surface. Notice these dark black arrows pointing towards each other. When these two air streams meet, the air is going to go upward in the atmosphere, and then you usually have a pocket of divergence aloft above that low-level convergence. Again, if this divergence is stronger, more mass is being removed or air is being removed out of the area aloft at the top of the air column that is being brought into the low levels, then you're going to have a intensifying cyclone at the surface or a deepening low pressure system. On the other hand, damper effect, we have upper level convergence. Notice how these arrows are coming together. As these arrows meet in the upper levels of the atmosphere, once they meet, the air is going to sink downward. In general, that's going to lead to low level divergence with the spreading apart of air at the surface, removal of mass at the surface. So you have to compare the rates of convergence in the upper levels in this case and divergence in the low levels to determine if you have a strengthening or intensifying high at the surface or a weakening high. If divergence aloft accompanies convergence at the surface, the resulting net transport of air aloft produces higher pressure at that isopycnic level, that level of equal density, requiring a temperature increase at that level to maintain constant density. So in general, what we're talking about here, we're getting back to the topic of the isopycnic level, the level of equal density. If you have divergence aloft, over an area of surface low-level convergence, the resulting net transport of air aloft produces higher pressure at that isopycnic level. And again, that's going to require, higher pressure is going to require a warmer temperature at that level to maintain that isopycnic level or constant density level. Air above 350 millibars must therefore subside to or sink to provide the required temperature increase. Any sinking air motion in the atmosphere is going to result in adiabatic warming or an increase in the temperature if air sinks in the vertical. Now that's going to give an upper air profile with heights decreasing above 200 millibars in the lower stratosphere and sinking air or subsidence from 200 to 350 millibars. This is going to produce an area of maximum horizontal divergence near the isopycnic level. So there's a lot of different dynamics that go on. When we live here at the surface, we think about, is it raining? Is it a nice day? But there's a lot of dynamic processes that are occurring above our heads. And this is a great example of that. And then we flip it around here and we say, on the other hand, let's say we have divergence at the surface. That's going to be associated with high pressure at the surface. An upper level convergence aloft, that's going to cause the pressure at that isopycnic level of constant density, to decrease, and that's going to require the temperature to decrease at that level to balance it. So if let's say we have rising air motions from 350 to 200 millibars. Now 200 millibars is about 40,000 feet above the ground. We have rising motions in the higher portion, between these two layers in the atmosphere, that generally produce adiabatic cooling. Height increases in the lower stratosphere, and the required drop in temperature at that level is necessary to maintain constant density at the isopycnic level. And that is going to result in area maximum convergence at or near the isopycnic level. So again, vertical air motion can be a very complicated subject in general, but all these processes kind of work together. In this case, to maintain constant density, we have to allow the temperature and the pressure are directly proportional to each other in order to maintain constant density at the specific level, the isopycnic level. So whenever we have a increase in pressure, the temperature's got to increase. And as a result, the air is going to sink. As air sinks, it warms. That's going to allow the isopycnic level to maintain that constant density. On the other hand, if we have pressure at that isopycnic level dropping or falling or decreasing, that's going to require a temperature decrease. How do you get temperature to decrease in the atmosphere? You get rising air motion that undergoes adiabatic cooling. Final result is going to be a circulation model where you get two vertical circulations, one above and one below 350 millibars. Now, by the way, 350 millibars is generally, 300, 200. Yeah, it's generally about 35,000 feet above the ground. The lower cell is going to show air rising in a cyclone, then moving laterally toward the anticyclone where it subsides or sinks. And an upper cell is going to produce a flow where air subsides or sinks in the stratosphere above the developing cyclone and rises above an anticyclone. So you get these upper air height decreases, for example, at that 40,000 foot level at 200 millibars, that accompany areas of surface convergence, and low pressure and upper height increases or rises accompany areas of surface divergence and high pressure. So what is this last bullet? The most important thing to take away from this slide is you get upper air height falls. Upper height falls accompany areas of surface convergence and lower pressure at the surface, and you get upper height rises that accompany areas of surface divergence and high pressure at the surface. All right, that wraps the training up tonight. Now, I know we kind of ended a little bit on a more complicated topic when we talk about isopycnic levels and the level of equal density, how to maintain that constant density. Let's just do a quick review of what we covered this evening in general. All right, so we started with the convergence divergence process, and convergence and divergence in the atmosphere occurs in two ways, either via directional or speed processes. Okay, we talked about directional divergence generally being associated with divergence is generally also known as bifluence. That's generally associated with air flowing outward away from a single point due to wind direction. Directional convergence, also known as confluence, that occurs when the wind direction comes together. The winds are kind of pointing towards each other, and that results in converging air toward a single point. Then we talked about speed convergence versus speed divergence, and I use the analogy of the toll booth in the cars. Speed convergence occurs when air parcels travel from regions of high velocity to low velocity. Even just thinking about driving on the interstate, if let's say you're driving 60 miles per hour and the guy ahead of you is only driving 50 miles per hour, you eventually are going to catch up to the guy ahead of you, and that's an example of speed convergence. Speed divergence occurs when air parcels enter into regions of higher velocity. So this would be a case where you're driving on the interstate, and let's say you're doing 55 miles per hour. The car ahead of you is doing 70 miles per hour. That car ahead of you eventually is going to open up distance or spread further apart or away from your car because he's going way quicker than you are. That's an example of speed divergence. We're just associating that real-life example with air parcels in the atmosphere. We also talked about the spacing and shape of these iso heights or isobars in general at the surface, helping to determine the flow of air. We talked about removal or additions of mass due to divergence and convergence, but there are times where we have the two opposing forces acting opposite to each other, and we have to analyze the station plot for the height tendencies, whether they rise or fall, to really determine if a convergence or divergence process, which of the two is most dominant at a specific point. We also talked about the connection of the low levels of the atmosphere, our surface highs and surface lows, in connection with the upper levels of the atmosphere, the divergence and convergence, setting up these direct and indirect circulation cells. Then I covered the chimney effect, generally associated with this low pressure at the surface and low level convergence, rising vertical air motion, removal of divergence aloft or mass aloft. In this case, this example, we had speed divergence as a reason why more mass was being removed at the top of this column. If you got accelerated divergence aloft, then you're going to have increased convergence at the surface, and that's going to result in much more vigorous rising vertical air motion, which is going to cause your storm system to intensify at the surface. Then I talked about the opposite effect, the damper effect. This generally occurs when we get upper level convergence above an area of low level divergence. Damper effect is associated with fair weather and surface high pressure, low level diverging airstream. Then I talked about a level of non-divergence, LND, a very important level in the atmosphere, in the mid-levels of the atmosphere, where maximum vertical motion or vertical velocities occur, whether we're talking about downward directed subsiding air associated with upper level convergence, high pressure and low level divergence, or whether we're talking about rising vertical air motion associated with a low pressure system in the low levels, in the convergence in the low levels, and divergence above that. Another important thing about level of non-divergence is it's that transition line between the two processes. Convergence in low level, above level non-divergence, I have divergence. In this case, I have low level divergence associated with high pressure. Above the level of non-divergence, I have upper level convergence. So it's the change from divergence to convergence across that level of non-divergence. Talking about the Isopycnic level, generally it's about 35,000 feet at 350 millibars above the ground, where you have density remaining constant. However, in order to keep that density constant, you have to have both temperature and pressure changes. And it's a directly proportional relationship. If temperature increases, then the pressure must increase. If temperature decreases, the pressure must decrease. Okay. Talk a little bit more about vertical air motion. Generally what happens, rising air is going to undergo adiabatic cooling. Subsiding or sinking air, adiabatic warming. And then another review on chimney and damper effects. And then I finish tonight's topic by talking about how you mean that constant density at that 350 millibar level. You generally, in this example, if we have divergence aloft and you have low level convergence at the surface, You generally are going to have higher pressure produced at that isopycnic level. Therefore, it's going to require a temperature increase at that level. So therefore, the temperature or the parcels of air, the vertical air motion is going to be to sink or subside, because as that air sinks and subsides, it undergoes adiabatic warming. And that's going to allow some of these upper level heights to decrease, in this case, above 40,000 feet, above 200 millibars in the lower stratosphere. And then finally, to conclude tonight's training, we just did the opposite effect here to maintain that equal density at the isopycnic level. In this case, we have divergence at the surface, accompanied by upper level convergence. That's going to cause the pressure at that isopycnic level to decrease or fall, requiring a temperature increase at that level to balance out. And how do you get the air to cool? Through vertical rising air motion, adiabatic cooling. And height increases occur in that lower stratosphere in order to maintain that constant density. And then finally, the circulation model overall. Everything is connected from the surface to higher up in the atmosphere aloft. Remember that. Three-dimensionally, you're going to have divergence over convergence or convergence over divergence. You really need to take a look at your upper level charts to see what's going on with your height tendencies at specific stations, upper air station plots, to determine if you have height falls or height rises, and whether you have divergence or convergence processes, which of those two is most dominant at a particular point in time. Generally, when you have falling heights, remember this, if you have a negative sign, falling heights on the station plot, in the upper air station plot, then you have a divergent process. Most likely you'll have low-level convergence of some sort and potentially stormy weather with low pressure. On the other hand, if you do the opposite effect, you have rising heights, you're generally going to have convergence being the more dominant process at a specific point in the upper atmosphere, and upper-level convergence generally yields sinking air motion and fair weather associated with surface high pressure. So everything is connected in a three-dimensional aspect from the surface to aloft. And I will have another video. We'll talk about upper air waves, short and long waves. That's coming down the line as well. I've got a lot more exciting weather training videos to share with you. I can't wait to share them. Hopefully you're getting a lot out of these training videos. You're just curious about knowing about how the weather works, or maybe you're studying meteorology at a college or university. Hopefully these videos are really good for you to really grasp what's going on. All right, so that wraps it up. Part 6, How the Weather Works training series. I'm meteorologist Matthew Euler. I thank you so much for subscribing to the Spot on Weather YouTube channel and taking the time out of your busy days and your busy lives to watch these trainings. Everybody take care. Until next time, God bless everyone.